The homework was number 1 through 6 on page 7, I think. 6 was included, wasn't it? Okay. And got my solutions over here. So, Claire, do you have a one you want to go over?
4.
Which one? 4? Yeah. Did you say 4?
4.
4. Okay. Yeah. So this one, this is the one. I don't know. Didn't I tell you? Don't worry about that one, and but come back to it. So this is a tricky one, and it's more just. It's going to be hard to wrap your mind around it, and really intuitively understand it. The explanation is more of a just use the formulas, plug and chug, and look at what you come out with in the end. So let me explain what Mr. Chase is doing here, and try to give you a little bit more background on it. So this is how rockets generate their thrust. Here's a rocket, and some fins on there, so it looks like a legitimate rocket. And this is the exhaust coming out. So it's Newton's third law. The rocket pushes the exhaust this way. So this is the rocket's force on the exhaust, and the exhaust exerts a force that way. So that's one way to think about how the rocket goes forward. The other way is just to think about this as an explosion of two things. Or you're going to do a problem. Let me just this will give you a preview of the problem that I think people find hardest on the homework. There's a terrible drawing, but this is a child in a boat, and the child is holding a package, and the child throws the package to the right. So this would represent the before picture, and then the after picture, the child's still in the boat, but the package is now flying through the air this way really fast. So in this situation, or the previous situation, everything is still. All the velocities are still. Nothing has any momentum. But in this situation, now the package is being thrown to the right. So guess which way the kid and the boat are going? To the left. And so that's what's happening. You can think of the rocket as doing the same thing. It's throwing the exhaust backward, and the exhaust is pushing it forward. And after the notes today, you can think of this as conservation of momentum, where if you have zero momentum to begin with, and then you have something with some positive momentum after some event, then that means you're also going to have something with some negative momentum. All right, so that's just the basic background. The rocket pushes the exhaust pushes the rocket. And this force right here, this could be thought of as the force of the rocket pushing the exhaust, or it could be the force of the exhaust pushing the rocket. But what does he say in here? I guess that's what we're looking for in the end. So it doesn't really matter if we're finding the force on the gas or the force on the rocket. The time period is, well, there is no time period, and that's what's tricky. There's not a time given. The mass, there's no mass given either. We've got a mass here, but it's a rate of mass. So it's 1,500 kilograms per second, which just means, okay, 1,500 kilograms for the first second, then another 1,500 kilograms for the next second. That's how much fuel is being thrown out of here. So this throws out 1,500 kilograms of fuel every second. And this is how fast it comes out. And there is a velocity there. So if you just tried to plug stuff in, you'd have trouble. But what Mr. Chase does is he divides both sides by time. So on the left side we have force times time. If you divide that by time, you get force. On the right side we have mass times change in velocity. If you divide that by time, you get mass times change in velocity over time. But you can factor out just this part. You can say this whole thing is equivalent to velocity times mass per unit of time, which is what we're given here. this is the rate of mass ejection. So I can plug in that 15 kilograms per second, or 1500 kilograms per second right here. 1500 kilograms over seconds, over 1 second, and then multiply that by the velocity, which is given, and that should give me the force. So it's just playing around with the impulse formula to get a rate of mass, so we can use that. But in terms of a great satisfaction of understanding how it all comes together, it's just you throw the numbers in and then you come out with that, and that's about the best I can do for you, other than saying this is what's really going on, you know. Other questions? Does anybody have a question about any of these other ones? The last class wanted to know why these two speeds, 39 and 52, were added up to get 91. Anybody curious about that? Sort of. I mean, it's just the...
Like when you're subtracting two,
well,
minus negative something, you got it.
Right. But the way that comes into play is with the change in velocity. And the way Mr. Chase is envisioning this is that the pitcher throws the ball to the batter this way. So I'm going to say it's going negative 39 meters per second. And then the batter hits the ball, and it goes back to the right at 52 meters per second. So the ball goes from 39 to the left to 52 to the right, which is a change of 91. If you add on 91 meters per second to negative 39, you get positive 52. So this hitting that ball pitched from the pitcher at 39 meters per second going back this fast would be equivalent to putting the ball on a tee and hitting it and sending it from 0 to 91 meters per second. The change in velocity would be the same for the ball. More questions? Anything about the homework? Okay. So back a couple of pages to page 3. Conservation of momentum. So if you see conservation of momentum, or just conservation, we've done conservation of energy recently. You probably did conservation of mass in chemistry. It just means the total stays the same. So momentum is conserved when certain requirements are met. And what that means is the total momentum, the total mv, if you take everything's mass in a whole system and multiply it by its velocity and add it all up, that total is not going to change in a closed system. So here's the formula. Let's just say the objects, I'm going to call them, we could call them A and B, we could call them 1 and 2. Oh no, I'm going to call them A and B. So just suppose there's an object A and an object B. So object A in the before picture would have a mass of A, and it would have its velocity. So its mass times its velocity, that's its momentum. And the other object, object B, would have a momentum of the mass of B times the velocity of B. And then they could collide with one another, they could explode apart, they could do whatever. And as long as this is a closed system, which means there's no outside force on the system, then that has to, let's add something, I'm sorry. MA initial, VA initial, MB initial, VB initial. Sorry about that. Then all that equals MA final, VA final, plus MB final, VB final. I did this with, instead of A and B last class, I did it with 1 and 2, and I've decided I like 1 and 2 better now. But you just need to have something to designate which mass are we talking about. And this could look like let's just suppose we have a couple of asteroids out in space. This is asteroid A, and this is asteroid B. And maybe A is moving this way and B is moving that way. So A, we would take whatever its mass is and multiply that by whatever its velocity is. And then after they hit one another, it's still probably going to have the same mass, probably, but it'll have a different velocity. And this formula, it gets to be big and kind of messy, but it's really easy. An isolated system is defined to be one in which the net force acting on the system is zero. And I think that was the same definition basically as the conservation of energy formula. Well, I don't know. Anyway, that's zero. For an isolated system, since the net force times time, which is impulse, equals the change in momentum, when the net force equals zero, the change in momentum equals zero. So what that's saying is, if there's no net force acting on this system, then this total amount of momentum is going to be equal to the total amount of momentum in the after. And now an example. I want to draw this picture first, and I'm not going to make the mistake of drawing it on that sheet of paper like I did before, because it took too much space. But I want to see if you can just don't try to solve this yet, but see if you can intuitively guess what the answer is going to be. I've got a 3 kilogram object, and it's got a velocity of 2 meters per second. It's going to crash into an object traveling with a velocity of negative 5 meters per second. So I don't really know whether this should be a big or small object. I'm just going to draw it about the same. And I know it's going this way, and the velocity is negative 5 meters per second. So this is the before. In the after the collision, the 3 kilogram object has a velocity of 1 meter per second, and the other object has a velocity of 2 meters per second. So the question is, what's the mass of this object? Think it's going to be smaller?
Yeah,
Smaller than that one?
Otherwise, because the 3 kilogram object has to be heavy enough to keep itself going in the same direction while also pushing the other one into an opposite direction.
And what is the fact that this is going fast? What does that tell you?
It's got to be lighter.
Right. So if this is fast and heavy, then it would overpower one that's not quite that's heavy and not quite as fast, right? But this one, if this is a contest where the goal is to keep going like you're going, this one's winning. So this one probably has more momentum to the right than that one does. But the momentum, the conservation of momentum formula makes this really easy to calculate. So I just got to add up the total momentum before and set that equal to the total momentum after. So we have 3 kilograms times 2 meters per second. That is, if I call this object A, and I'll call this other one, the other object, call that object B. So MA initial times VA initial is 3 times 2. And for object B, I don't know what the mass is. I'm just going to say, I'm actually going to call this, yeah, I guess I'll just call it MB, times negative 5 meters per second. So this is total momentum in the system. And that's got to be equal to the total momentum after the collision, which is 3 kilograms times this new velocity, 1 meter per second, plus mass of B, which we still don't know, times its new velocity, which is 2 meters per second. 3 times 2 is 6, and what would the units be for momentum? Kilograms meters per second. Just what it says already. Kilograms meters per second. And this is going to be negative 5. I'm just going to say, actually I can't really simplify that much. I'm just going to write it exactly like it was written before. mb times negative 5 meters per second equals 3 kilograms meters per second plus mb times 2 meters per second. So now I want to combine like terms. I'm just going to subtract this from both sides. So on the left side I've got 6 minus 3, which is 3 kilograms meters per second. And I'm going to add this to both sides, or I'm going to add 5 meters per second times mb to both sides. So I get on the right side mb times 7. Sort of screwy the way I did that. Does that bother anybody? Let me rewrite that. You can leave that if you want to, but I'm going to rewrite this in a way that I think just mathematically looks more sensible. So I'm going to call this minus 5 mb meters per second. And I'm going to call this 2 mb meters per second. And then I'll add 5 mb meters per second to both sides, so I get 7 mb meters per second. Still kind of funny. So if I want to solve for mb, I just divide both sides by 7 meters per second, and mb equals 3 kilograms. Oh, wait, no, 3/7. 3/7. 3/7. Which is, how many is that? Got it in my notes. 0.4243. 429. All right, I'll just call it 0.43. Which is kind of what we thought. It's quite a bit lighter than this. So it's just bouncing off. And that's it. That's it for conservation of momentum. The practice questions are page 8. It's basically everything on page 8. And I think it might be useful before we do that. I mean, if you want to ignore what I'm about to do now and just kind of start working, that's okay. But I want to go over a few example scenarios like this, just to try to get you comfortable with what's going on. So anybody who's still with me, what I want you to do is anticipate what the answer is probably going to be. Last class, a lot of people got this one wrong. Suppose you've got a really heavy cart. Let's say it's I won't give it an exact mass, but it's like this much, and it's going pretty fast. And then you've got a lighter cart that's running away from it, but not as fast. So this is fast and heavy, and this is light and a little bit slower. This is going to catch up to that, and when it does, they're going to stick together. They're just somehow going to hook on, or one way or another get stuck, and then they're going to move together. So my question for you, is this going to be, how does the speed of this compare to these? Here we've got something, this one's faster and heavier, this one's lighter and not as fast.
So it's slow down.
So the big heavy one, is this faster or slower than the individual heavy one was in the beginning? So this is going to be moving slower than that was,
Is it in between the speed of the two?
in between the speed of the two.
Like subtract the speed or something.
That-
I think add them
So just whatever you're thinking, let's put some numbers to it and then figure it out. So this, if each of these is a kilogram, this would be 3 kilograms,
I guess it was, yeah.
and this is 1 kilogram. And so altogether, this would be 4 kilograms. And let's just say this is going 1 meter per second, and this is going 2 meters per second. So what do you think? Is this going to be going faster than 2, in between 1 or 2, 1 and 2, or less than 1? I don't know. I'm not telling.
Well, I mean, normally if there's more weight, it means you're going faster. But it's confusing because those two are supposed to equal that one. So you would think we'd be going slower. So I don't know.
All right, so here's I'll just solve it mathematically. So we can use conservation of momentum. The total momentum before equals the total momentum after. And the momentum of this is the mass times the velocity, which is 6 kilograms meters per second. And the momentum of this is the mass times velocity, which is 1 kilogram meter per second. And so that's 7 kilograms meters per second. And that's got to equal the total momentum after. So the mass of this is 4 kilograms. What's the velocity? 7 fourths. So 1.75 meters per second, which is a little bit slower than this. So this is going to hit that one. And the fact that this is slower is going to slow this one down a bit. But the fact that this one gets hit by that one is going to speed this one up. And which one changes speed more? The heavier one or the lighter one? The lighter one, because it's got less inertia. Another kind of situation that's going to pop up a lot is explosive situations. And when you get to the question about the boat, this is really what that one's like. Suppose you have, this is going to be a 2 kilogram cart, and it's stuck to these are wide, so they must be heavy. This is 8 kilograms. That's not very fun, but anyway, this one's 2 kilograms. And somebody puts a little bit of explosive right there, and then they end up flying apart from one another. So the one on the left is going to the left, and the one on the right is going to the right. And this one's going 3 meters per second. How fast is that one going? So can anybody guess what it's going to be just without even doing any math?
5.25.
Alright.
What do you think? Is 5.25 correct? So the total momentum here is what? How much momentum do they have before the explosion? Maybe I didn't explain this very well. They're not moving. The velocity is 0. Velocity is 0. What's the total momentum? 0. So that means the total momentum here has to be 0 also.
Oh, so it's 0.
So -3, you think?
No, wait.
Exactly.
-9.
-9. This is 8 kilograms, and this is 2.
12 times 12.
Yeah, -12. So the total momentum here equals 2 kilograms times the velocity of this plus 3 kilograms. Oh, sorry, 8 kilograms times the velocity of that, and that all has to add up to 0 because the total momentum doesn't change. So this is 2 kilograms times v equals plus 24 kilograms meters per second. So 2 kilograms times v equals negative 24 kilograms meters per second, which means v has to equal negative 12. And Claire, so what was your reasoning, Claire, without doing the math? Why'd you think this was going to go 12? Oh, so you did the math.
Mentally.
Yeah, Claire just did that in her
That's what I
head.
was shouting out right away.
Right.
I
And,
was trying to do the math.
and another way to think about it is that they need to have equal and opposite momentums. And if this has 4 times the mass of that, then that needs to have 4 times the velocity of this. So 4 times that velocity is 12 meters per second the other way. All right, I won't take any more of your time. There's a video if you need any help on this. The one people have the most trouble with is number 10. So people at home, you're welcome to stay and